Or are you just switching to the PDF? Oh, okay. Okay. Okay, hi everyone, sorry for the delay. I'm the next speaker. I'm Doug Markant. I'm going to start off with a couple of quick questions you can answer for yourself as quickly and accurately as you can. First, which planet is further from the sun, Venus or Neptune? Okay, probably pretty easy. Okay, same question, which is further from the sun, Jupiter or Saturn? So how did you answer these questions? Well, there's a good chance that you've learned some internal representation, some map-like representation of the solar system, and you can consult that to make comparisons between any two objects, right? A well-known marker of that kind of representation is the symbolic distance effect, which is just that you're faster to make comparisons between objects that are really far apart in that representation, like Venus and Neptune, while nearby comparisons like between Jupiter and Saturn are slower and more likely to produce an error. Where did that map come from? Well, the solar system is a pretty simple physical system, and there's a good chance that you learned about it with the benefit of an actual map or a diagram like this one. But we can, of course, form cognitive maps to organize knowledge about all sorts of stuff, including more abstract domains. For example, the structure of our social environments. So to illustrate that, let's consider another couple of questions. With my apologies, this requires that you think a little bit about US politics. First one, which politician is more powerful, Nancy Pelosi or Alexandria Ocasio-Cortez? Probably pretty easy to answer. And then last question, who's more powerful, Joe Manchin or Kirsten Sinema? So yeah, you probably answered the first one pretty quickly, whereas you might have taken a little bit longer to answer the second one. You might be a little bit more uncertain. The point being that over time, there's a chance that you form some kind of a cognitive map to organize your knowledge about the social system, US politics, which incorporates this kind of abstract quality like power or influence, and which you can use to then make judgments or predictions. And importantly, you learn this in bits and pieces over time. So you didn't have the benefit of a physical map or a diagram to organize that knowledge. So the project that I'm going to talk about today is focused on this question of how we form these kinds of abstract cognitive maps of relational systems by combining together related experiences. And this work relies on a common paradigm for studying this question, which is transitive inference, where people have to integrate a set of premises like A is less than B and B is less than C in order to draw inferences like, for example, that A is less than C. So the talk is going to have two parts. First, I'm going to talk about the results of an experiment, looking at how some training sequences are more effective for people to build up this kind of a cognitive map. In particular, chained training sequences, like the one that's shown at the top right here, where you're seeing overlapping premises from trial to trial. And then I'll present some modeling work that tries to see if we can account for this effect of chain study and talk a little bit about what that means for how we build cognitive maps. So first, I'll describe the basic setup in the task before I talk a little more about the rationale for the experiment. So in the task, people are instructed to learn about the chain of command at a 9-person company. And during the training phase, they study premises consisting of all of the adjacent pairs of individuals drawn from that hierarchy. So for example, on the trial shown at the bottom left, the person on the left is directly supervised by the person who's shown on the right. And they continue this until they reach some training criterion. They then proceed to a test phase shown at the bottom right, where for every possible pairing of individuals from the hierarchy, they have to judge who's ranked higher in the chain of command. And this test crucially has these inference trials where they have to make comparisons between people who they had never experienced together during the training phase, right? So they have to draw these larger inferences. And as I mentioned before, with those examples at the top, typically what you see is the symbolic distance effect, where people are really fast and accurate about people who are really far apart in the hierarchy, and they're slower and they make more errors for nearby inferences. So in some recent studies using this kind of task, I found that people who could actively choose which premises to learn about preferred to create chained sequences of premises, right? So when they had the power to select which premises to see, they created these overlapping sequences from trial to trial. And this is consistent with the idea that people are trying to construct some unified representation of the hierarchy, and chaining together those premises helps them to integrate them together into this single map. But in those studies, there were some other differences between training conditions that could have contributed to the effect. So in this experiment, the goal was just to directly manipulate whether people experienced overlapping premises from trial to trial, while holding constant the spacing and the relative frequency of the premises. So there are two conditions. In the chains condition, as you can see here, the training sequences were always had overlapping premises from trial to trial, whereas in the jumps condition, the premises were presented with the exact same frequency, the same spacing, but there was no overlap between successor trials. So if creating a cognitive map benefits from this kind of temporal contiguity or this overlap between premises, then you'd expect performance to be better in the chains condition compared to the jumps condition. And this is, in fact, what we found. So this plot is just showing the performance on that final test in each condition as a function of the distance between the two items. And in the chains condition, accuracy is really high across the board, whereas in the jumps condition, accuracy is a lot lower. And you can see there's more of a kind of distinct symbolic distance effect where people are pretty bad at nearby inferences and they get better and better for more distant inferences. So these results, in conjunction with the previous studies, suggest there's really a pretty robust effect of chain study in transitive inference. Chaining seems to help people to build up this integrated representation of the hierarchy. So in the rest of the talk, I'm going to examine whether we can account for this effect using a couple of computational models that have already been applied to similar kinds of transitive inference studies. So in the paper, in my Coxide paper, I compare, two models from Kamaran et al. In 2016. The first is a particle filter. Particle filters are a technique for sequential Monte Carlo approximation to Bayesian inference, where the posterior distribution is approximated with a set of discrete samples. I'm going to walk through that in some more detail in a second. And then the second model is called RL-ELO, which is a non-parametric method for estimating ranks based on the outcomes of pairwise matchups, like the kind of things people are experiencing in this task. And this uses an incremental updating rule of the sort that you'd see in reinforcement learning models. I'm not really going to have time to talk about the second model in the talk today, so I'll just tell you up front that this model ends up not being able to account for this effect of chain study. So I'm going to focus on the particle filter. So the goal of the particle filter is to infer the locations of all of the items along this continuous dimension as you observe the premises. And knowledge of the hierarchy is represented as a set of these discrete particles, each of which you can kind of think of as being like a different hypothesis about where the items are located. So at the top right, there's an example with 5 particles. Each of the dots is a different item located in a different spot. It's also helpful to look at these density plots that gives you a sense of the state of the model's knowledge about where this particular item is located and how much uncertainty there is. So for that example with 5 particles, there's a lot of uncertainty at the end of training, and the average positions of the items don't even really line up that well with the true ranks. But if you increase the number of particles, like shown at the bottom right, we start to get more precise estimates. So that's an example with 40 particles where the average positions are now pretty much in line with the true ranks. And if you were to continue increasing the number of particles, then you're going to converge closer and closer to what the fully kind of Bayesian solution would be for the task. So that's what the model state looks like by the end of training. How do you get to that point? What does learning actually look like for the model? So on each trial, you start off with some existing state. This is now a very simplified kind of cartoon toy example. You start off with an existing state, like those 4 particles shown at the left and the positions of the items. Then you evaluate the likelihood of a new premise that's observed, like the one shown at the top, A is less than B. In the paper, I talk about 2 different likelihood functions that I explored. The first one I refer to as local updating, which is very simple. It's just based on the difference between the positions of the 2 items. So if I observe the premise A is less than B, and for a given particle, if A is less than B by a good amount, then it's going to have a high likelihood, right? If those positions are swapped, then that particle would have a low likelihood. The other form of the other likelihood function is referred to as global updating. So you might expect that people can actually learn a little more from these premises because they're instructed that they represent people who are directly adjacent to each other in the true hierarchy. for example, that person A is directly supervised by person B, and there's nobody else in between them. So this alternate likelihood is called global updating, where that prior knowledge is taken into account. And particles that have both the kind of correct relative position of the two items and where there's no other person intervening, those will tend to have the highest likelihood. Okay, after you evaluate the likelihood of the observation, then you reweight the particles according to the likelihood and resample. These are just kind of standard steps in a particle filter. I tried to make as few assumptions as I could since there are some degrees of freedom. This resampling has the effect of filtering out particles that have a low likelihood that can't account for the observed premises, while particles with a high likelihood will proliferate. And then the last step is referred to as propagation. Oh, sorry. Yeah, that's the resampling. Yeah, where you're duplicating the high likelihood particles. And then the last step is propagation, where you randomly perturb all of the positions of the items across all the particles. And this allows the model to kind of continue exploring for alternative solutions for all the orders. So the main question I addressed in the paper is, can the particle filter, which has been previously applied to a similar social hierarchy learning task, can it account for this seemingly robust effect of chain study without assuming any other differences between the conditions? So the models were trained on the same training sequences as what people saw in the chains and the jumps conditions across a wide range of parameters, including across a range of numbers of particles, across different amounts of random fluctuation from trial to trial. And then lastly, comparing the local and the global likelihood functions. So turning to the results. So the plots at the top are showing on the x-axis is increasing the number of particles in the model. And then the y-axis is just showing overall performance on the inference test. And the first thing that we see is that performance improves as you increase the number of particles. This is kind of like a gut check. You want to see that as you increase the representational capacity of the particle filter, you're kind of converging toward what the fully Bayesian solution would be. The lines on the bottom are showing that there's relatively poor performance if the model isn't able to explore enough. So if there's not enough random fluctuation in items positions, then you would require lots and lots more particles to get to good performance. So that random fluctuation is actually really important for these models to achieve good performance. All right, and now for the key result, performance is much better in the chains condition compared to the jumps condition, as shown on these positive values on the bottom. So this is true for a relatively wide range of parameter values, but the advantage is greatest for a relatively small number of particles peaking around n equals 40. And then as you keep on increasing the number of particles, that advantage decreases until you get to the best performance with a huge number of particles, and there's no difference. So in terms of overall performance, there's a clear advantage from chain study according to the particle filter. Another important question is just whether the model can predict the same pattern of results that we see for people. So as a preliminary test of this, oh, sorry, I keep forgetting to advance. As a preliminary test of this, I just found the parameter combination that minimized the root mean squared error between the model predictions and human performance. And the predictions looked like this. And this captures the qualitative pattern of results that we saw for humans. In particular, performance is relatively flat and high in the chains condition, and there's more of a distinct symbolic distance effect in the jumps condition. Again, this is somewhat preliminary, and more work needs to be done to fit the model to individual participants, but it's encouraging that the model can produce the same kind of qualitative pattern of results. All right, so why does chaining have this effect for the particle filter? So to answer that, it's helpful to kind of visualize the trajectories of the model state over the course of training. So these lines are showing the average estimated positions of each item in the aggregate across lots of different runs of the model. And the little jags that you might see on the left-hand side are the responses to observing new premises, right? Where the estimated positions of all the items are starting to fan out and get pushed out. You can see that in the chains condition, it achieves the correct ordering of all the items relatively quickly. In comparison, in the jumps condition, that happens a little bit for the items that are kind of at the two ends of the hierarchy, but the items in the middle just kind of keep on fluctuating back and forth, and you don't get this same separation of the positions. Okay, so I'm going to wrap up quickly with a couple of takeaways. So first, the behavioral study adds to evidence of this clear advantage of chain study and transitive inference, where experiencing these overlapping premises helps people construct an integrated representation of the hierarchy. I think this is kind of an example of a more general principle that learning about an unfamiliar system is easiest when it's incremental, when you can connect new observations to something else that you've experienced recently. So that idea in and of itself maybe is not all that new, but there's still lots of questions about how to formalize it and how it's expressed within a computational model of this kind of learning of cognitive maps. So the particle filter captures a lot of the patterns that we see with human behavior. And it suggests that especially early in learning, our knowledge of this kind of a system is uncertain and it's in flux. And that fluctuation can be good because it's allowing us to continue to explore for the right solution. And chain study helps to manage or to shape that kind of exploration during the early stages of learning. And with that, I think I'll end there and leave time for a question or two. Okay, thanks. Okay, I think I left a time for one question if there's anything.
Thanks for that nice talk, Doug. I just wondered about the relationship between the chained and the jump to the massed versus spaced effects that you see in discrimination learning. So somewhere in between the chained and the jump could be AB, 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 AB,
right,
followed by BC, BC. Do you know what I mean? Whether you've got any insights as to how that would fit in with the effects that you've got here.
Yeah, so this is a typical training pattern that you see in the transitive inference literature, but the training works a little bit different in that often you'll start off with one discrimination like AB, you'll do massed study on that until you reach some criterion. Then you'll add in BC, for example, and kind of continue in that way. There have been direct comparisons of this actually in humans. I think there's at least one study showing that when you interleave all of the pairs, which is essentially achieving a similar thing to the chaining, then it's better compared to when you have these blocked or masked study of the premises. Yeah. I think for the similar reason that, especially for this type of task, participants know what they're trying to do, right? They're trying to organize this cognitive map, and the chaining is most effective for that goal. Yeah. Okay, I think we'll move on to the next speaker. Thanks, everyone. Next up is Abhilasha Kumar.